Hello friends, in this video I will discuss the first lecture on modern physics, which is a course in different undergraduate programs and named as engineering physics, modern physics or relativity. And we discuss the first lecture of relativity, and the topics covered will be frames of reference, inertial and non-inertial frames, and Galilean transformation equations. So we will discuss about the physics before year 1900. That time mechanics was fully developed, and it was by Galileo and Newton and other scientists. Optics were also known, and electricity and magnetism were also developed by Coulomb, Oersted, Ampere, Faraday. And electricity and magnetism was correlated by Maxwell by giving the electromagnetism. And thermodynamics was also well developed by Carnot, Kelvin, Clausius, Joule, etc. So that time these branches of physics were well established, and they were explaining most of the phenomena in nature and in physics. But there were some problems in the physical laws when the objects were moving with very high speeds as comparable to the speed of light c. So in that case, then Einstein gave the theory of relativity to explain such phenomena. Also, there were some phenomena like black body radiation, which was not explained, and later Planck gave a quantum theory, which we will discuss in quantum mechanics later. So this whole course is about modern physics, which means that it was developed after 1900, and after that, using these theories, modern physics, quantum mechanics, and quantum field theories, and nuclear and particle physics were developed. So in this unit, in this course, we will discuss the topics of modern physics. So classical physics or classical mechanics is not applicable when the bodies move with velocities near to the velocity of light, or when v is equivalent to c. Then there are some new concepts due to the relativistic theory. The length of moving body contracts in the direction of motion, that is known as length contraction. Also, there is one effect that is known as time dilation, means clocks in motion, they get slowed down, and mass also changes with velocity. So mass of a moving body is greater than its mass when it is at rest. So usually we take these quantities as constant in classical mechanics, but here we will see that using relativistic theory these quantities also changes. So relativistic mechanics is the branch of physics which deals with the objects which are moving with the speed of light or equivalent to the speed of light, and it is divided into two parts. First is special theory of relativity, and it is for the objects which are moving with the constant velocity, or the acceleration is zero in that case. If b is constant, and if we acceleration means dv by dt, that is zero. But general theory of relativity is applicable to all kind of motion, whether the velocity is not constant, or for the accelerated motions also. So length, position, time, mass, these all are relative. So suppose we talk about the length. If we can say that we have two lines, and line B is bigger or taller than A. But we cannot say that B is the biggest or tallest, because if we compare it with a third line C, then B is smaller than C. So length is always uh, relative. Time in India and other countries of the world are different, so time is also relative. Mass and size are also relative. Suppose we compare a tennis ball with an atom or a nanoparticle which have dimensions in angstrom or nanometer. And if we compare with the tennis ball, which have diameter in few centimeter, then there is, we cannot say that tennis ball is biggest, but it is, as compared to nanoparticle, it is 10 to the power 7 or 8, 10 to the power 8 times bigger. But if you compare the tennis ball with earth, then it will be, again, earth is around, the diameter is 12,000 kilometer, so it is 10 to the power 8 times bigger than tennis ball. Similarly, if we compare earth with sun, so we cannot say earth is the biggest, because if we compare it to some other object, then so it all, size and mass, these all are relative. Also the position is also relative, because if we have on table, we have one triangle and one circle is there, so A will tell that this triangle is on right side, but B will tell that this triangle is on his left side. So it is, the position is also relative. So observer A and B will tell different positions, so it is also relative. And special theory, it was proposed in 1905 by Albert Einstein in the article on the electrodynamics of moving bodies, and this paper was in German, published in Annals of Physics in 1905. And the term special was used here because it is the special case used for only inertial reference frames, means the frames which are moving with constant velocity. And after this special relativity, there were a lot of phenomena was explained, like E equal to mc square, that matter and energy are correlated, and we will discuss in later lectures. And special theory of relativity is also important tool to describe the interaction between elementary particles. And the general relativity, it takes care of the acceleration also. So theory of gravitational and other effects are also included in general relativity, and it was published in 1915 by Einstein, and it is valid for any kind of frame of reference, and it is used in astrophysics, cosmology, and GPS systems, etc. Now we will discuss some of the terms which will be used throughout this unit. One is frame of reference. A frame of reference is a coordinate system which tells us about the position of an object or an event or a particle at a particular time. And inertial reference frame are those frame of reference in which the Newton's law of inertia or other Newton's law are valid, and in such a frame the body is either at rest or it is moving with some constant or uniform velocity, or it should be unaccelerated, means acceleration is zero because b equal to constant. And the examples are like a building or a lab or a car or a train moving with constant velocity, means b is equal to constant. And usually earth have spin and orbital motion, and for an observer on its surface, usually we take earth as inertial frame of reference. Also the acceleration is very small in case of the spin of the earth, so usually we take earth as inertial frame for the observer on earth. And non-inertial frame are those frame of references in which Newton's laws are not valid and acceleration is not zero. In this case, a is not equal to zero. So suppose a moving train or car which is changing the velocity, or if brakes are applied, then there will be acceleration is not zero. And earth, usually earth have some kind of acceleration, very small acceleration, and usually we take it as inertial frame or for the person which is on earth, but we can take the earth as non-inertial frame for the person which is observing from the moon or some another planet. So in that case, Earth can be treated as non-inertial frame. Now, what is Galilean invariance? So Galileo was a scientist who gave some kind of equations, and it is in classical mechanics. If Newton's law is valid in one reference frame, then they are also valid in another reference frame, moving with a uniform velocity relative to the phase system. Means these, if in inertial systems, so Newton's law are valid in all the frame of references, and this is referred as Newtonian principle of relativity or Galilean invariance. So means if the laws are valid in one frame of reference, it should be valid in another inertial frame also. So this is known as the Galilean invariance or Newtonian principle of relativity. So here we see the laws of physics are same for the observers in different inertial frames. Suppose here the train is at rest and this ball is going in this frame, and if the train is moving with some constant velocity, then also this ball is going in this frame. So observer is inside the train in both the cases. So laws of physics are same for the both the observer, either it is at rest or moving with some constant velocity. And the position of observer is very important. We will see in this example that if there is a moving truck and a person throws a ball upwards, then for him it is a vertical path. The ball goes up and comes down to him. So because it is moving with it is moving with constant velocity, it is inertial frame, and the observer is with the moving frame of reference. So for him it is just a vertical motion. But if the observer is outside of this truck, suppose observer is on the road and this truck is moving with constant velocity, then the path of this ball will be curved for this observer on the road. So it is, and the person will look like a parabolic path. So that's why the position of observer is very important. So two observers, which is with the frame, moving frame, and one was in observing from another frame of reference from the rest, then the path of ball looks different for different observer. And now we will discuss the Galilean transformations, and these are the set of equations which relates two frame of references. And suppose one frame is S, which is at rest, and another frame is moving with some constant velocity v, then how the coordinates of some event P or point P, objected as point P, then how the coordinates are related for the moving frame to rest frame. So these equations are known as the Galilean transformation equations. And if point P have coordinates x, y, z, and t, because here we have to also take the time also. The space coordinates are x, y, z, and time coordinate is t. So for this point P at a particular time, the coordinates are x, y, z. So we will denote the coordinates of this point P for an observer at rest or in stationary frame S frame. For observer O, the coordinates are x, y, z, and t. But if the now the this system have moved in x direction, so the coordinates of this point P will be changed for this moving observer O dash or O prime, and in that case the coordinates, let us say that these are x prime, y prime, z prime, and t prime for the observer O prime, or we can say that x dash, y dash, z dash, and t dash for this O dash, and it is S prime frame or S dash prime which is moving with some constant velocity B. So now we have to Galileo gave some equations which relates the coordinates of this moving frame to rest frame. With using this equation we can understand that if the motion is only in x direction, for simplicity we take the motion in x direction only, s and s prime were at the same point at t equal to t prime equal to 0. Initially they were at the same point O here, and uh, now this s prime is moving with some constant velocity v. So in t time it have moved some distance b into t. So for the observer this x distance, it was initially it was x from for this s observer the distance was of this point p was x, but now it have traveled some distance bt. So now the new distance for this observer is x prime will be x minus bt. So now we have a relation in x dash and x. So this kind of equation was given by Galileo to uh, get a relation in moving frame to rest frame, the coordinates of one frame of reference to another frame of reference. So this was Galilean transformation equations. And if we take the the movement only in one direction, in x direction only, then the coordinates will change. X prime will be x minus bt, and there is no motion along y and z axis. So y axis and z axis there is no motion. So y prime will be y, z coordinate z dash will be z, and time t prime equal to t. So in Galilean transformation equations, there are some conditions. It is we valid for the parallel axis, and the frame should move with constant velocity, and usually time t prime equal to t. So all the observers the time is fundamental invariant, means time is same for all inertial observers. So time in this frame should be equivalent to this frame in the Galilean transformation equations. So t prime equal to t. So these are the relation how the coordinates of moving frame of references, means primed coordinates, are related with non-primed or the without dash. So x prime x dash with x, y dash with y, z dash with z, and t dash with t. How these are related due to the relative motion b. So x prime will be x minus bt if motion is in x direction. If we take the motion in y direction, then only y coordinate will change, other coordinate will be same. Then x prime will be x, y prime will be y minus bt. So depending on in which direction there is motion, we can use these equations, which are known as the Galilean transformation equations for space and time. Space coordinates are x, y, z, and time is t. So now using the Galilean transformation, we will get the velocity transformation, and we know that these are the Galilean transformation equations between x prime, y prime, z prime to x, y, z, and t. And if you differentiate this equation number 1, dx prime by dt will be dx by dt minus b with respect to time t. And then we have to put t prime equal to t, means we can replace dt by dt prime. So dx prime by dt is dx prime by dt prime. So it will be, we can write it as equation number 6 as ux prime equal to ux minus b, and there is no motion along y and z axis, so uy prime equal to ui, and uz prime will be uz. And generally we can write u dash equal to, or u prime equal to u minus b. So u prime is the velocity in the moving frame, and u is the velocity of object in rest frame, and b is the uniform velocity of the frame of reference. So these are the Galilean velocity transformation equation, and it gives us the relation between the primed velocity to non-primed velocity. Primed means moving velocity to velocity in the stationary frame. Now we will see the acceleration transformation, and for that we need to differentiate the velocity equations. And if you if we differentiate this ux prime with dt, du x prime by dt will be d by dt of ux minus b, and b is constant, so it will give us dux by dt. And if we replace dt by dt prime, so ax prime will be ax. Similarly, ay prime will be ay, az prime will be az, because we can replace this dt by dt prime. So in general, a prime equal to a, so acceleration is invariant under Galilean transformation. So inverse Galilean transformation equations, these are used when we know the primed coordinates. If you know x prime, y prime, z prime, t prime, means the coordinates in the moving frame of reference, and we want to get x, y, z and t, the coordinates in rest frame, then we can use the inverse Galilean transformation equation. For that we need just have to replace b with minus b, so it will be x equal to x prime plus bt, y equal to y prime, z equal to z prime, and t equal to t prime. These will be same. And now what is invariancy of an equation? So by invariance of two equations means the equation will have the same form when determined by the two observers. And invariance of an equation means then after applying a particular transformation, the equations should remain the same. And we can prove that Newton's second law is invariant under Galilean transformation equation, because we already know that F equal to ma, it is the Newton's law in suppose rest frame of reference, so it should be F equal to m into a prime in another frame of reference, because we have already seen a prime was uh, already invariant, so that's why mass is constant in Galilean transformation equations or in classical physics. So if a is a prime equal to a, then F equal to this. If we differentiate the acceleration a prime equal to a, this we have already done in last slides. So F equal to F prime equal to m into a prime, that is ma. So it is in same form as it was in the rest frame. So that's why we can say that Newton's second law is invariant under Galilean transformations. Now we have one another examples, that we have to prove that electromagnetic wave equation is not invariant under Galilean transformation equation. So wave equation is second order partial differential equation, which is delta 2 pi by delta x square plus delta 2 pi by delta y square plus delta 2 pi by delta z square minus 1 by c square delta 2 pi by delta t square, or it should be equal to 1 by c square delta 2 pi by delta t square. So we have to prove that this is not invariant, means if we replace with it primed coordinate delta 2 pi by delta x prime y prime square plus z prime, this all in primed coordinates, so this should be not in the same form as here it is. And phi is a coordinate of phi x y z and t, or phi is a function of x prime y prime z prime and t prime. So we have to first differentiate this phi with respect to x two times. Everything we have to differentiate with uh, two times and use the Galilean transformation equations. And so first, suppose for first term we want to get delta 2 phi by delta x prime square. So for that we need to know first delta phi by delta x, and delta phi by delta x can be written because phi is a function of x prime, y prime, z prime, t prime also. So delta phi by delta x can be written as delta phi by delta x prime into delta x prime by delta x. So it is just chain rule. We can write this delta phi by delta x like this: delta phi by delta x, delta y prime, delta y prime, delta phi by delta x, delta z prime, delta z prime, delta phi by delta x, delta t prime into delta t prime. So it is a function of these all x, y, z and t, or prime x prime, y prime, z prime and t prime. So we can write it in primed coordinate because we want a relation in primed coordinate to non-primed coordinate. So that's why we are doing this all in primed coordinate. And now we can put delta x by x from this equation. If we find the partial differentiation, delta x prime by delta x is equal to 1, because b and t will be treated as constant, so only this will give us 1. Delta y prime by delta y uh, will give us 1, but delta y prime by delta x, it will give us 0. Similarly, delta x prime by delta y 0, other things will be 0, and delta x prime by delta t will be minus b. So if we put values here, delta x prime by delta x, it is 1. Delta y prime by delta x, this is 0. Delta z prime by delta x, it is 0. And delta t prime by delta x, it is also 0, because in t prime there is no x. So with respect to x, these all values are 0. Only first term will give us 1. So it will delta phi by delta x, these other terms are 0. So delta phi by delta x is equal to delta phi by delta x prime. And if we delta by delta x, if we differentiate one more time partially, delta 2 phi by delta x square will be delta 2 phi by delta x prime square. So this first term is in same form as without prime. So delta 2 pi by delta x prime and delta 2 pi by delta x prime, x square, it is in same form in primed coordinate and non-primed coordinate. So now we will check for y prime also, and z prime and t prime, and then we can say whether it is invariant or not. So similarly, for the y coordinate also we will see that second derivative of y is equivalent to second derivative of y prime. So this is also equal. In the case of z coordinate, delta 2 pi by delta z square is also equivalent to delta 2 pi by delta z prime square. So now we try for the t coordinates, delta phi by delta t. First we have to find this, and then delta 2 pi by delta t square in terms of t prime. So we will see what happens. So delta phi by delta t can be written again by chain rule. We can write it in terms of x prime, y prime, z prime, and t prime using this. And delta phi by delta t will be, if we put delta x prime by delta t, it is minus b, and delta t prime by delta t will give us 1. So it is also, this term is also there, and other terms will give us 0. Delta y prime by delta t 0, delta z prime by delta t was 0. So that's why we have. Now if we remove this phi, then this operator delta by delta t, in place of delta by delta t we will write minus b delta by delta x prime plus delta by delta t prime. So if we have to differentiate one more time this equation, so we'll have to operate this by delta t, delta phi by delta x equal to minus b, this operator, into minus b delta phi by delta x prime plus delta phi by delta t prime. And if first we have to do operate with this first term and then operate with second term, and it will give us this term delta 2 phi by delta t prime minus 2b delta 2 phi by delta x prime delta t prime plus b square delta 2 phi by delta x prime square. And we can see that this term delta 2 pi by delta t square is not equivalent to delta 2 pi by delta t prime square. There are some extra terms. So if we put all the values of primed coordinates in this equation number 1, then we will find that there are some extra terms. So left hand side does not equal to right hand side equation, because space coordinates are showing the correct form, but time coordinate have some extra terms. That's why we can say that this electromagnetic wave equation is not invariant under the Galilean transformation. So this was that's why there was some problem with the Galilean transformation equations, and there were some reasons of failure of Galilean transformation equation, that it failed to explain the electromagnetic waves traveling with the speed of light, like we have seen in last question, that electromagnetic waves, they do not follow the Galilean transformation equations. And Maxwell equations were also not invariant under the Galilean transformation equations. And it also could not explain the Michelson-Morley experiment, which we will discuss in next lecture. And these equations are valid for low velocities, but they fail to uh, the objects which are moving with the speed equivalent to speed of light or very high speeds. And the modification in these equations were done by Lorentz after the Einstein's postulates, and these modification and these Lorentz equation which are valid for all kind of velocities. So we will see these in future lectures. So thanks for watching this video, and if you have any queries or suggestion, then please write in the comment box. And in next video we will discuss the Michelson-Morley experiment, and which was a failed experiment, but it gave the ideas to many scientists, and then there was the new theory developed. So we will discuss these all in next video. And if you are new to this channel, then please subscribe this channel. Thank you very much.